Hey, so welcome to Brian's crash course on PageRank, where I go over PageRank at a high level because it's kind of missing a little bit from our assignment page. But for the sake of completeness, I'm going to first go over TF-IDF vectors a little bit, and that is on the assignment page here. That's like this section, so I think this describes it pretty okay, but well, I'll just go over it again anyway, and even briefer. So a TF-IDF value is essentially just a way of measuring the importance of a word in a document. Now, importance here accounts for both the frequency with which that word appears in the document, and when I say document, I just mean pretty much a bunch of text. So words that appear often in your text are probably more important, and we also account for how often words appear in all documents. The reason behind there is, for example, words like the and a, those probably appear in pretty much every single document that you might find on the internet. And words that appear that often usually carry less meaning and are thus less important to our document. So we decrease the importance of those terms. And in our case, the documents are web pages, and we use TF-IDF vectors to gauge the relevance of our search terms to our web pages. So we pretty much get the TF-IDF values of all words, we put those all together into a vector, and then we compare the vectors that we got for our search query and all of the vectors that we got for all of our web pages, and we find the one that's most similar to our search query, or well, we rank them really, because we probably want more than just one result in our search engine. So that's TF-IDF. Now, PageRank is completely independent of TF-IDF vectors. They're really not related at all. PageRank is a way of measuring how popular each web page is, and it doesn't depend on your search query at all. So we can combine TF-IDF vectors with PageRank to get the most popular web pages that are also related to your search query. So this way we don't end up with search results where the web page just repeats your search query a bunch of times, because that's probably not what you're looking for. So I think the easiest way to understand PageRank is by drawing an analogy to something more physical, something that is really not the same, but probably easier to understand. So imagine we're at, imagine we're at a carnival. So we have a couple attractions, say we have a parking lot. Wait, whoops, that's gonna disappear. Let me fix that. Here we go. Alright, say we're at a parking lot. So this is our parking lot. Or sorry, we're at a carnival. The carnival has a parking lot. And the carnival also has food stands. How do I draw that? It's like this. Yeah, sure. And there's like wheels on it. The food cart. Yeah. And then we also have a circus. Circus looks like this. It's pretty circusy, right? And then maybe we have a Ferris wheel in the back here. Beautiful. Alright, so we have these 4 attractions, and let's say we want to model the popularity of each of our attractions. So, of course, visitors can be at any of our attractions at any given point in time. We're going to say the popularity is just how many people go to that attraction. So what we essentially do is we build up a graph, because that seems like it would be a reasonable thing to do here. So we'll say our attractions are vertices, and our edges are just how people can move between the attractions. So we'll say that in this carnival, there's no way to get to the Ferris wheel without first going through either food stands or the circus. And actually, I'm gonna write this out. So vertices are attractions, and edges are just physical space. So to make our lives easier, we will impose a couple restrictions on our model. So the first one, we'll say that we have discrete time steps. So our visitors have to stay at each attraction for a whole time step at a time. And also, at the end of a time step, they have to move. They have to transition to some adjacent state, adjacent attraction, that is, or vertex. So we also do want visitors to be able to stay in the same place. And to achieve that, we'll just add self loops to our vertices. And maybe in our parking lot, we don't want visitors to stay there for more than one time step at a time, because I don't know what you're going to do in a parking lot for that long. So we just won't add a self loop here. And the other thing that we want to add now to our model is some metric of transition probability. That is, say I'm at the Ferris wheel, how likely am I to stay at the Ferris wheel to take this self loop, versus how likely am I to move to the food stands here, or the circus. So each of these edges gets some probability in our graph. So that'll pretty much just be an edge weight. So we'll say maybe there's a 0.5 probability of staying the Ferris wheel, and there's like a 0.2 going to the circus, and 0.3 of moving to the food stands. So the restriction we've added here is that these probabilities are the same across all time steps. So, regardless of whether it's your first time step being at the Ferris wheel or your 100th time step here, it's the same probability of staying on the Ferris wheel or moving off to the food stands or the carnival. And also note that the way that we've formulated this there's an equal probability of leaving the Ferris wheel, whether you're, at the bottom of the Ferris wheel or if you're at the top of the Ferris wheel. That's just not something our model has handled. So yeah, there's a chance that we jump off the Ferris wheel randomly and go to the food stands. So that's just something that we will accept, just a simplification to make our lives easy. And also note that now that we've added these weights, these are actually the weights from the Ferris wheel to somewhere else, right? So that means that our edges are now directional. So what we need to do is pretty much turn all of our edges that we've drawn into directional edges that go both ways. I'm not going to draw these all on this graph because that makes things very messy, but just pretend that these all exist. So this kind of model is called a Markov chain. That's the details there are out of scope for this class because Markov chains are not data structures and they're also not algorithms, and this is a data structures and algorithms class. But essentially, a Markov chain is characterized by this kind of dynamics where you have some finite number of states and you have discrete time steps where at each time step the probability of transitioning between any two given states is the same across all time steps. So that's exactly what we have here. Now, how do we use this model to simulate visitors? Well, the way we go about that is we first initialize some number n of visitors just randomly across our carnival, just uniform distribution. So we have I'm going to draw dots for visitors because that's probably the least cluttered way to do this. So we've evenly distributed our 16 visitors across all 4 attractions. So this is what the state of our graph looks like at time t equals 0. And now we just step through our graph, or rather step through time in our model, where at each point in time each visitor transitions from their current state, their current attraction or the current vertex, to some adjacent vertex according to the probabilities that we have written on our edges. And we would have probabilities on all of these, but again, that adding in those numbers just clutters things up, and just pretend that they exist here. So maybe at time t equals 1, our visitors, we would expect half of the ones on our Ferris wheel to stay here, and then the other half, maybe one goes here and one goes here. And then we do the same for our carnival. Some numbers stay here, and then some number goes here, and so on. And we keep on repeating this process out to infinity time steps. So it actually turns out that in this case, we have a kind of well-formed graph here. And in this case, as t approaches infinity, we'll get to some stable equilibrium where the attractions that are more popular will end up with more people, and the ones that are less popular, like probably this parking lot, will end up with fewer people. the math behind that statement is, again, a little bit out of scope for this class, so just accept that that is okay in this case. Now, I did say that this is a well-formed graph. We will see in a little bit an example of where that is not true, and then we have to fix that, but I'll get to that in a little bit. First, what are the implications of this model? So essentially, the popularity of each attraction is just going to be defined by the transition probabilities of all of our edges, and that's apparent because, well, those are the only things that affect the movement of visitors in our carnival. But at a kind of lower level, if we look closer, each attraction is going to be affected by the number of attractions that are adjacent to it, so the number of incoming edges that it has. So like, here, there's three places that you can get to the food stands from, whereas for this parking lot there's only two. But also important is the actual weight on those edges. So if only 0.1 of the people from the carnival go to the food stands, that's probably not a huge contribution to the popularity of the food stands. But also, one more thing that we have to consider is how popular each of the adjacent attractions are, because if the carnival isn't very popular, then its contribution is going to be even smaller. Whereas, for example, if our probability, coming from the parking lot is 0.5, 0.5 and 0.5 each way, but the parking lot is itself not popular, even though this probability is high, the actual number of visitors this represents is very low, because just nobody comes from the parking lot, nobody's here to take this path. So let's put web pages into the same framework. So in the case of web pages, then we have our vertices would be web pages. Yeah. And our edges now are hyperlinks. Now note that hyperlinks are kind of innately directional. They only go from one page to the next and not the other way around, as compared to our physical space, which, well, if you can get from point A to point B in this carnival, you can probably also go the other way around, unless you had to jump off a cliff to get places, which is probably bad carnival design. So yeah, I'm gonna draw out an example graph for web pages now. So let's say we have Wikipedia here. This is the Wikipedia logo. It looks something like this. There's pieces in the logo, and then maybe we have Google like this, right? And then you have your grandma's website where she posts pictures of her cats. Yeah, that's a cat. So, and really here, Wikipedia is not just a single web page, it's actually just many web pages. But for the sake of not cluttering up this graph, we will focus on this one web page that maybe it links to your grandma's site for some reason. And Google probably links to Wikipedia, and there's a bunch of edges here. And do I want to draw arrows on these? I should be, but like it's only makes them messy. But yeah, something like that. So this is what the internet looks like. Now, again, we are going to impose some restrictions on this model. In this case, we're actually going to say that the probability of transitioning from one page to the next is the same for all outgoing edges from a web page. So, for example, we'll look at this page. So, if this page has a link to this page, and also one here and one here, each of these has a weight of 1/3. So again, that's just a simplification we've made to make our lives easy, and just kind of in practice, as a search engine, you would not be able to tell how popular, the real value of each of these transition probabilities. So just to make a somewhat reasonable guess, we'll just say they're all the same. So what does this mean? This means that now the popularity of your website is just affected by the number of websites that link to it, and also of the websites that link to it, the number of other websites they link to, and also the popularity of that website. So pretty much the same thing as before, except now our edge weights are dependent on the number of things that you link to, the number of outgoing edges the page has. Now, there are actually some things that come up immediately in this graph that we did not have before, and that would be this here. So we'll notice that your grandma's web page does not link to any other web pages. So what does that mean for our simulation? So, our people are going to be wandering around on the internet, and then maybe sometime they take this link to your grandma's site, and now they have nowhere else to go. So they're just stuck here for the rest of eternity. So in this case, what we want to do is say, if users end up stuck at some edge with no outgoing edges, we will just at the next time step throw them out somewhere random into the internet again. So just any web page with the same probability, you just end up somewhere. And this is just pretty much a hack or a band-aid fix to keep users moving in our simulation. The mathematical correctness is like, well, I don't know, it really doesn't make a lot of sense in the model, but it works out in practice. So that's what really matters. And there's also a similar case that isn't quite in this graph right now, but you can imagine that, say, your grandma's site linked to some other site, and that site only links back to your grandma's webpage. So now, instead of a single dead end, we have kind of a dead end cycle, and you're never actually stuck at one node, but you're also never going to leave this part of the graph. So what we do in this case is pretty similar to what we had before. It's just we assign a probability, some small probability, that at any given point in time, any user at any node will jump to somewhere random in the internet. So that means that if you end up in this cycle, then eventually at some point you'll just teleport somewhere else into the internet and leave the cycle. This also means that even if you're on Google, sometimes you will teleport somewhere random and well, end up elsewhere. So again, kind of weird in terms of our model, but it makes the numbers work out. So that's the important thing. So that's pretty much that for PageRank. The actual implementation details are, of course, on our assignment page. We have that's what here, yeah, that's these here. Make sure to expand the expando things. I'm not actually sure what these are called, but do click these. There's good stuff in them. And yeah, I think that's about it. If you have more questions, feel free to ask on the discussion board or in office hours. Yeah, I can't think of anything else to say. I'm going to stop this recording now.